Okay, folks, we're going to take a look at acid and base properties now. Anytime we're talking about acids, I always want you to picture lemons, okay? And anytime we're talking about bases, I want you to picture cleaners while we're talking about the properties of acids and bases. So when we think about how an acid tastes, of course, we would say that it tastes sour because we know that citrus fruits and things like that taste sour, okay? And bases have that bitter taste, and that bitter taste is that taste you taste at the back of your mouth, kind of on the sides of your tongue when you get shampoo that runs down in your mouth, that is a bitter taste. Okay. In comparison to water, we would say that acids actually feel like water. Now, if it's a concentrated acid, of course, it may feel kind of burny, but in terms of the texture, it has the same texture as water. Okay. Bases have a much different texture to them. If you were to dip your fingers into a base and then feel your fingers, it's going to have a slippery texture. Okay. It's going to feel like soap between your fingers. Okay. So when we ask, do they conduct electricity? If we remember back to the last unit, we remember that both of these are actually electrolytes. And an electrolyte tells us that yes, something does indeed conduct electricity. Okay. Um, if we take a metal and we add it to an acid, it will react in the form of making bubbles. It'll make hydrogen gas, and bases do not react. Okay. Phenolphthalein is an indicator that we use. If I add a drop of phenolphthalein to an acid, it's going to remain colorless. And so, like magic, I have this acid that has appeared right here. And if I take some phenolphthalein and I add one drop of phenolphthalein to it, then magic, oh, look at that, it stays clear, okay? So when we add phenolphthalein to an acid, it stays clear, okay? Now, when I add phenolphthalein to a base, oh, look, there it is, it's nice and clear. I add my phenolphthalein drop, and oh, like magic, it turns pink. Isn't that awesome? Yes, it is, okay? So now, in terms of what acids and bases do with litmus paper, I know that acids are going to make litmus paper turn red. So check it out. I've got some blue litmus paper here, pretty awesome. And when I add this blue litmus paper to an acid, oh, like magic, check it out. It turns red. Okay, so that's what happens when acids come into contact with litmus paper. When bases come into contact with litmus paper, okay, they start off red and then they turn, you guessed it, they turned blue, okay, just like that, like magic, okay? So that is what acids and bases do with litmus paper. In terms of their pH scale, we already talked about this on the last video. pHs less than 7 are going to be acidic, and pHs greater than 7 are going to be basic. Okay, also, our acids are going to contain more H plus ions, and bases will contain more hydroxide ions. So there are some properties of acids and bases that you can think about while you are dealing with acids and bases. Now, also, we have a few definitions that I want to discuss in this portion of the notes. The first definition is that of what a buffer is, and a buffer is a solution which resists changes to pH. Let's think about this for a moment. If I have an acid and I add a base to it, it's going to cause the pH to rise. However, what a buffered solution does, let's say I have a solution of a pH of 1. If I have a buffered solution and I start adding base to it, that pH is going to remain constant, okay? Now, of course, there is a breaking point. Basically, what the buffer is doing is it's eating up the base. As the base is entering, it's eating up that base, and it's not allowing it to affect the pH. But there is a breaking point. So at a very finite point, that pH is going to go 1, 1, 1, 1, 1, 1, 1, 1, 1, and then it's going to spike, okay? So that's what happens when you reach a spot where your buffered solution cannot fight off the base anymore. Okay, blood is a perfect example of a buffered solution. We have a couple more definitions. First, we have amphiprotic. What amphiprotic means is that a substance can behave as either an acid or a base according to Bronsted-Lowry. So Bronsted-Lowry says that acids are losers, meaning they lose protons, and bases are gainers, meaning that they gain protons. So if a substance can gain or lose a proton, it's considered to be amphiprotic. So let's take a look at water. Water can gain a proton to become a hydronium ion. Water can also lose a proton to become a hydroxide ion. Therefore, water would be considered an amphiprotic substance. Um, Also, we have a situation called polyprotic, and a polyprotic acid is an acid that has more than one hydrogen that it can lose. So if you ever look at your formula and you see on your formula that you have multiple hydrogens, you know that that acid is polyprotic. So HCl would not be polyprotic, it would be monoprotic because it only has one hydrogen. Hydrosulfuric acid, H2S, this would be polyprotic. This would be, take a guess, monoprotic. And this would be, take a guess, polyprotic. Okay, so there we go. That's the difference between monoprotic and polyprotic.